Hello, hello. So today we're going to be diving into a little bit of chapter 9. But today's section is actually doing things that you've done in previous classes and just getting those back to the forefront of our mind so that when we get into what we're doing in chapter 9, that we already have these things ready. So today, Section 9.0, you're going to probably want a notebook. Since we haven't gotten our new notes packet yet, we're just going to do notes in a notebook. Section 9.0, and in this section, we are squaring binomials and simplifying square roots. Yay, I got it to fit there. Okay. So, today you're going to see a couple different things, obviously, by the title. The first thing you're going to be asked to do is to simplify some basic binomial multiplication. And binomials are polynomials with two terms. In other words, things that have variables and numbers getting added, subtracted, or multiplied. And we've done this a little bit already in this class. We've had some of these binomials getting multiplied together in our proportions. And when we do it, we're just doing large distribution. Everything in the first parenthesis gets multiplied by everything in the second parenthesis. We don't do this if there's some sort of like exponent on the parentheses, like an exponent out here. But these don't have that. So this is where FOIL comes into play. So I take this 3x and I'm going to multiply it by both the 2x and the 6, starting with the 3x. 3x times 2x, 3 times 2 is 6, and x times x is x squared. So that's 6x squared. 3x getting multiplied by the 6 is a positive 18x. Negative 6 getting multiplied by the 2 is a negative 12x. And negative 6 getting multiplied by a positive 6 is a negative 36. After I've done this, I combine my like terms. Remember, like terms, same variable and the same exponent. So that 6x squared does not get combined with anything. Just those two. Keeping in mind that since they're on the same side of the equal sign, specifically, there's not actually an equal sign here. Technically, I could have put one here. But when they're on the same side of an equal sign or there's no equal sign, combining is just doing exactly what this thing says. In this case, it says positive 18x minus 12x. 18 minus 12 is 6. So positive 6x minus 36. This should look familiar. We've done this before. When people tend to get a little tripped up is when we're squaring binomials. So that's like x minus 5 quantity squared, because what people want to do is square the x, square the 5, and move on, but you cannot do that. You cannot put an exponent on all of the things inside the parentheses unless inside the parentheses there is only multiplication and division going on. Since I have a subtraction here, in order to do this, I have to think about it as x minus 5 getting multiplied by x minus 5, because that's what squaring is you multiply something by itself. And then we distribute. X times x is x squared. X times negative 5 is negative 5x. Negative 5 times x is negative 5x. Negative 5 times negative 5 is positive 25. And I combine my like terms again. Negative 5 and negative 5 goes together to give me negative 10. We're going to do one more. 3x plus 7 quantity squared. Now at this time, I encourage you to pause and try this one out on your own. See if you get the same thing as me. I can't force you to do that, but I would recommend doing that. So if we do this, we multiply it by itself. And we distribute. 3x times 3x is 9x squared. 3x times 7 is 21x. 7 times 3x is 21x. And 7 times 7 is 49. Combine like terms, and I get 9x squared plus 42x plus 49. Now this is the squaring binomials piece of the notes. We are also going to be simplifying square roots. So, technically our instructions were already simplify, but I'm going to write it again because it's a slightly different simplify here. Now the first few examples are gonna be very, very simple. So I'm just gonna write them across here because the first few examples are a special type of example, and they're the easiest of the problems to do. So these are what we call perfect squares. And what that means is these numbers that are inside the square roots here, they are numbers that are the result of squaring a number. So by taking the square root, I'm essentially just asking what number got squared to give me 121, for example. But since 121 is a perfect square, that means that when I type it into my calculator, I get a nice, easy number to work with, 11. The square root of 16 is 4. The square root of 225 is 15. So simplifying square roots when they're perfect squares is real simple. It's about putting it into a calculator. But if I wanted to simplify something more along the lines of the square root of 32, if I typed that into my calculator, I would get 5 point something. It would be a lot of decimals. And to get 5 point something would not be a simplified version of this. That would be evaluating. Evaluating is when you just figure out what it is as a straight number if you typed it into the calculator. Simplifying is different. Simplifying means put it in its simplest form, with square roots. If they're not the square root of a perfect square, that means getting the smallest number possible left inside the square root. And anything that you can pull out of the square root, you need to. In order to do this, you need to know your perfect squares. So along the right side here, I'm going to make a little table of perfect squares. So I've got x and I've got my x squareds. Now 1, I can square it. I get 1. It's not helpful. So I'm going to start at 2 in my little table. And 2 squared is 4. 3 squared is 9. 4 squared is 16. And I'm coming up with these numbers. The regular x's, I'm just counting. The squared numbers is to square something's to multiply it by itself. Or I could just type squared into my calculator. 5 squared is 25. 6 squared is 36. 7 squared is 49. 8 squared is 64. Okay, I'm going to go a little bit further with my table. 9 squared is 81. 10 squared is 100. 11 squared is 121. And 12 squared is 144. Now I could keep going forever, but for what we're doing here, these perfect squares are going to be plenty. Now, if I want to simplify a square root, essentially what I need to do is I need to figure out which of these perfect squares divides out of the thing I'm trying to take the square root of. Now, specifically, I want the biggest number it divides by. So that means generally, for me, what I do, if I'm trying to simplify the square root of 32, for example, I look at my table of perfect squares and I say, okay, where would the 32 fit? It would be in between these. And then I start, oops, I put it in the wrong spot. It would be between 25 and 36, don't mind me. And then I start checking the number smaller than it. And I say, okay, does 32 divide by 25 nicely? And if I know my perfect squares, or my divisors, my factors, that becomes really easy. And I just ask, well, no, 32 doesn't divide by 25 nicely. If you don't know, that's okay. Just grab a calculator and start dividing. 32 divided by 25 is 1.28. If it's not a whole number, it doesn't divide by it. 32 divided by 16 is 2. So once I figure out the biggest one that it divides by, then what I do is I take that square root and I say, okay, 32, square root of 32 is the square root of 16 times 2, which I can break up into 2 separate square roots. Now, one of these is a perfect square. The square root of 16 is a nice perfect square to work with, and it simplifies. It becomes a 4. And I still have this square root of 2 next to it. And I can do this process as many times as it takes until the number inside the square root is as small as it can possibly be by dividing by perfect squares. Since 2 doesn't divide by any perfect squares, that means this is my simplified form. Okay. Let's try another. Square root of 108. So 108 would fit right here. 108 does not divide by 100, does not divide by 81, does not divide by 64, does not divide by 49, but it does divide by 36. It is 36 times 3. Break it up into 2 separate square roots then, and I simplify the one that was the perfect square. Square root of 36 is 6. Now 3 also doesn't divide by any perfect squares, so that is it. Accidentally turned my pen off. There we go. Now sometimes you're going to see a number in front of the square root. And that's okay if you see a number in front of the square root. You still do things the exact same way. $180. Now 180 is bigger than these. In fact, it's bigger than some perfect squares that are on there. But I'll actually give you a hint. A square root cannot divide by any number bigger than half that number. So I technically don't have to start checking this or checking the perfect squares it divides by until I get to at least as low as 90. So I don't have to check anything bigger than 90. That being said, we're also not trying to trick you and give you obnoxious perfect squares. 2 through 12 squared are going to be plenty big. And if they're not plenty big, you can always make this list longer. It's just squaring things on your calculator. Now, for the record, sometimes when you do this, you don't necessarily get the biggest perfect square. Sometimes we accidentally miss one because we skip over one. So I want to talk about that real quick. Let's say you accidentally missed one. Now, 180, it does divide by 4. It's 27 times, sorry, not 27. It's 45 times 4. I don't know where 27 came from. 4 is the perfect square. So it becomes 7 times square root of 45 times 2. And that number in front doesn't change anything we do. We just follow the same process that just has to travel along with. Until then we start multiplying whole numbers together and square roots together. There's only 2 whole numbers. Those can get multiplied together, and you always put the integers in front. So you get 14 times the square root of 45. But 180 did actually divide by a bigger perfect square, and I should have divided it by a bigger one. If I ever miss that, here's the way that you can check that. 45 still divides by a perfect square. And if the number inside the square root does still divide by a perfect square, then you just do the process again. You don't have to undo what you did to find the bigger perfect square. You just say, okay, well, 45 divides by 9, which is a perfect square. So I'm going to put 14, and it's 9 times 5. So I can break it up into 2 square roots right away. You'll notice that I tend to actually skip this step. And square root of 9 is 3. So I got 14. I've got 3. I've got a square root of 5. Remember that it's times between all of these. And 14 times 3 is 42. So if you ever end up where the stuff inside the square root still divides by a perfect square, just do it again. 5 does not divide by a perfect square, therefore this is what I get. If you're ever not certain of your answer either, if you're like, I don't think I did this right, then type your original problem, in this case, 7 times the square root of 180, type that into your calculator, and your new problem, 42 times square root of 5. In both cases, I get 93.91485505, and then it keeps going. If you get the same thing for both of them, then you've got the same number. It can't guarantee that you've got the most simplified form, but at least it establishes that you didn't screw up the problem. Now, that being said, we're also going to end up with situations where they ask us to simplify something more like this, 5 over the square root of 5. Because one of the things that's a rule in mathematics is that square roots cannot stay in denominators, or any sort of radical for that matter, which is any sort of root. And denominator is the bottom of the fraction, in case you've forgotten that. So if you ever run across a problem where you have a square root in the denominator, we have to do what's known as rationalizing the denominator. And to rationalize the denominator is essentially mess with the problem so that the square root's not on bottom. Now, in order to get a square root out of the bottom, in order to get rid of a square root, people often think of squaring it. But the problem with squaring something is you change the number. So we're going to do what is essentially the equivalent of squaring the denominator without actually changing the problem. And that is, to square something is to multiply it by itself. So when you have a square root on the bottom of a fraction, you multiply the bottom of that fraction by the square root that's in it. Now, in multiplying this stuff, we multiply the top and the bottom. That way we're not changing anything. It's a fancy way of multiplying by 1, and multiplying by 1 doesn't do anything. When you multiply the top, most commonly you're not going to have a square root on top, which is perfectly fine. Whole numbers and square roots don't multiply nicely. They just sit next to one another. 5 times the square root of 5 is literally 5 times the square root of 5, 5 root 5. Square roots do multiply together. Just like we can take a square root that is things multiplied together and change it into separate square roots like we did up here, we can go and do the opposite as well. We could say take two things that are in square roots and multiply them together. 5 times 5 is 25. And since it was in a square root, it stays in a square root. Except our goal was to get the square root out of the denominator. But since we multiplied by the square root that was in the denominator, it's always going to become the square root of a perfect square. Square root of 25 is 5. And from here, we have to check if the fraction simplifies. The fraction simplifies if the square root divides by a perfect square, 5 does not, or if these two both divide by the same thing. In this case, they do. They both divide by by 5, making them both 1s once I divide them by 5. And I don't need 1s in front of things, nor do I need 1s in denominators. So it simply becomes the square root of 5. Okay, few more examples of simplifying and we are done. So 7 over 4 square root of 3. So first thing on this one I notice is there's a square root in the denominator. Can't leave that there. So I multiply both the top and the bottom by the square root that was in the denominator. That is the square root of 3. You don't need to multiply by the 4. The 4 is not a problem. If you do multiply by 4 square roots of 3, it'll work out the same. You're just going to have a lot more simplifying to do. Okay, 7 times the square root of 3 is 7 in front of a square root of 3. 4 square roots of 3 times the square root of 3 is 4 square root of 9, because the whole number doesn't multiply by anything because it doesn't have another whole number to multiply by. In all technicality, you could say there's a 1 right here, and 4 times 1 is 4. So remember, whole numbers with whole numbers, square roots with square roots when multiplying. Now, that square root of 9 in the denominator does simplify, so I end up getting 7 square root of 3, which was on the top, over the 4 that was already there, and the square root of 9 is 3. Remember, it's multiplication between these. And I can multiply that 4 and that 3. 7 square root of 3 over 12. Now at this point, once the square root's out of the denominator, I double check simplify. The square root of 3, well, 3 doesn't divide by any perfect squares. And I also check these, and 7 and 12 do not both divide by the same number. Therefore, this does not simplify. Our final answer is 7 square root of 3 over 12. again, just a couple more examples. Next one, 6 over the square root of 12. Square root in the denominator, that's a problem. Can't leave that. I multiply both top and the bottom by that square root. Remember, when multiplying, numbers outside of square roots and numbers inside of square roots do not multiply together. They just kind of sit next to one another. So 6 square root of 12 over square root of 12 times square root of 12 is square root of 144. And the square root of 144 does simplify. It is 12. In fact, you may have noticed that when I multiply a square root by itself, I always end up with just that number. Multiply the square root of 3 times the square root of 3, I ended up with just a 3. Multiply a square root of 12 times the square root of 12, I end up with just a 12. You are allowed to use that. Anyway, now I check for other simplifies. The square root of 12 does divide by a perfect square. Furthermore, the 6 and the 12 simplify. Now I'm going to deal with that 6 and that 12 first, just because I like working with smaller numbers. But I could go in either order. 6 and a 12 both divide by 6, leaving me the square root of 12 over 2. I do not simplify things inside the square root with things outside the square root either. Whole numbers with whole numbers, square roots with square roots. Now, square root of 12, as I established earlier, does divide by a perfect square. It divides by the number 4. It's 3 times 4 specifically. Square root of 4 is 2. Now keep in mind that even though I have the square root of 4 second, technically the whole numbers always go in front of the square roots. So when I simplify the square root of 3 times the square root of 4, it becomes 2 square roots of 3. Still over 2, and hey, I ended up with something that simplifies here again. They both divide by 2, giving me 1s, and I don't need the 1s in front of things or in denominators. So I end up with the square root of 3. Now, the last example that I'm going to show you just looks a little different. Just want you to see one like it. And that is something like the square root of 14 times the square root of 3. So, just to reiterate, square roots multiply with square roots, whole numbers with whole numbers. There are no whole numbers here, or technically there's the invisible ones that you don't necessarily need. But if there was, you would not multiply them with the 14 and the 3. Whole numbers with whole numbers. There aren't any. 14 times 3, square root of 42. Because they're both in square roots. Don't forget to put the square root. Now, 42 doesn't divide by any of my perfect squares. Like I could check. 42 goes here. Doesn't divide by 36. Doesn't divide by 25. 16, 9, 4. Doesn't matter. Sometimes a number inside of square root doesn't divide by any of the perfect squares. If that's the case, it's its most simplified form.